Hi everyone, my name is Mike, and I'm going to share with you 10 techniques I have for improving your group delay measurements on frequency converting devices that have embedded local oscillators. And by that, I'm talking about devices such as this MyTech satellite block down converter, which takes a 20 gigahertz signal into the back and mixes it with an 18.75 gigahertz embedded local oscillator and outputs a signal around 1 gigahertz. So I'm focused on measuring the group delay of a device such as this, and that's what I'm going to go through my 10 techniques for making the measurement as accurate and fast and easy as possible. So for my measurements, of course, I'm going to use the Rohde Schwarz ZNA vector network analyzer, which was introduced about 1 year ago, and this is an instrument that has been optimized for making frequency converting measurements. So in particular, I'm going to use option K9, which is our two-tone technique, which was created specifically for measuring group delay on devices with embedded local oscillators. And for more information on that topic, we have an application note, 1EZ81, which is titled Group Delay Measurements on Frequency Converting Devices. It goes through all the details, goes through the equations, and how to make the setup and measurements. So a lot of information is available in this application note. But we are interested in watching videos, so I'm going to go through my techniques for optimizing this measurement in the videos. In other words, you don't necessarily need the application note. Now, let's get started. In this video, I'm going to go through idea number 3, which is to optimize your power levels for making your measurements. Now, there's 3 reasons we need to worry about power levels and we need to optimize our power levels. The first one is, okay, every microwave device has a dynamic range, which means it has a compression point and it has a noise floor. So we need to stay into the sweet spot of this dynamic range. So for the vector network analyzer receivers, that means we can't be too high in power because we'll compress the receiver, but we also want to stay well above the noise floor so we have a good signal to noise ratio. For the device under test, we have the same challenge. We cannot overdrive the device under test, and we also have to be aware of not starving the device under test. I don't want my signals to be in the noise. So I'm worried about being too high, and I'm also worried about being too low in power. So now, I'm also creating a two-tone signal. Now, in the previous video, we talked about the different techniques we have for creating the two-tone signal, and I want to make sure I'm picking a technique and then leveling the tones so that I have the optimal signal-to-noise ratio. So in particular, my favorite technique for creating the two-tone signal is to use the coupler as a combiner. But when I do this, one of my two tones goes through the coupled arm of the coupler, which has 10 dB more loss than the main arm. So that means one of my tones is 10 dB lower than the other, and that's not fair to this tone. It's going to have a lower signal-to-noise ratio. So if we increase the power of that tone, then we will have a better signal-to-noise ratio on it, and it will make our measurements more accurate. Now, the other thing I have to worry about is if my device under test has a lot of gain or a lot of loss, because either scenario will take the port 2, the receiving port of the network analyzer, and put it at a higher power level or a lower power level than port 1. So that can be a concern. Now, during calibration, I'm going to use a mixer with a lot of loss. That means port 2 is going to be seeing a low power level, and I can take advantage of adding gain to the port 2 receiver or taking attenuation out of the port 2 path. On the other hand, if I'm measuring a device that has a lot of gain, then I will have to lower the power on port 1 so I don't drive the device so hard, and now port 1 will see a lower power level versus port 2, which will see a nice strong signal coming from the device under test. So I have to be aware of these different trade-offs, and I have to make sure I'm keeping everybody out of compression, port 1, the device under test, and port 2. Okay, and I also want to take advantage of getting the best signal to noise ratio possible. So this is the trade-off I'm going to make when I'm optimizing my power levels. Now, to help with this, I have an application card. It's called Test Set Options in the ZNA, and this describes where the different attenuators are located inside the instrument. You can purchase these attenuators as options, which will help you to optimize the power level at the port 1 receiver and the port 2 receiver. And it also shows you where the different settings are in the test set of the ZNA so that you can see what's happening as you change different parameters. So take a look at the app card for more details. But in the meantime, we're going to go through it on the instrument, and we're going to see what happens as we make some of these different changes directly during the measurement. So let's get started. Now, if you remember in video 1, I said, let's automate our measurements. That way we get the same settings every time. So we're going to take advantage of that in this particular case, and we're going to pull up an automated script that's going to create 2 channels, and we're going to use the 2 channels to compare what happens when we make changes. So the first thing I want to explore is what happens when I try to level these 2 tones. Does it really have an effect if one of the tones is 10 dB lower than the other? So let's take a look at that script first. Now I'm just going to run the script, and you have to trust me, it's doing the same thing that we've done in the previous videos. So let's go to the application key, select GPIB Explorer, make this full screen, and select the script which talks about step 3, transmit power, optimizing the power levels. Now, the script says connect the calibration mixer, and we're going to calibrate 2 channels under 2 different conditions. I've already connected the mixer, so let's take a look. Now, calibration is complete. So I have 2 channels here now that are under 2 different conditions. This first channel, I did not compensate the power of the source that's going through the coupled arm of the coupler. So I have a delta in my tones of 10 dB. In the second channel, I did compensate this, so I brought the second source up 10 dB in power, so now both tones have about the same output power, which improves the signal-to-noise ratio on the second tone, and you can see this second channel has slightly better performance. Now let's take a little closer look at the details, how I can confirm that what I just described is what's actually happening. So we select the first channel, and if we go to the measure key, some of the things we can measure are listed here, but the thing I'm interested in is the 2-tone group delay and power of these 2 tones. So if I take this first channel, which is highlighted, so it's active channel, and I drag this onto the screen, I can get a trace for one of the 2 tones. Now I can measure the 2 tones, the power of the tone at either the input to the device or the output of the device. What I'm interested in is the power at the input, because I want to level these 2 carriers that are offset from each other. So I'll pick the lower tone, so I get a trace of what the power is of the lower tone at the input to the device under test. And then I want to put another trace on this window, and I want to see the power of the upper tone. So in this case, if I place a marker on these 2 traces, then I see that these 2 tones are about separated by 10 dB. Because of the loss of the coupler, for one of the 2 tones, it sees 10 dB more insertion loss than the other tone. Now if I come down to this bottom channel, this is where I put the second tone, I brought its power up by 10 dB, and I repeat this measurement to confirm that it's doing what I think it's doing. I want to highlight channel 2, I want to go to measure, go to 2-tone group delay, and I want to drag a main tone onto the screen. And again, I want the lower tone, and I want another trace for the upper tone. Now we see these 2 tones are practically on top of each other. So this second channel, what's different in this channel is that I brought the tone power up by 10 dB. Now the way to do that is under the channel configuration, port configuration, there is a port settings dialog box. I can open this up, and in here there's a number of things that can be done. What I want to go to is the arbitrary power tab, and you'll notice that I took port 3, which is going through the coupled arm of the coupler, and I increased its power by 10 dB relative to port 1. So that's how I brought the power up on the second tone. That's the only change I made. And when I did that and calibrated, you see that my performance has improved from a peak-to-peak variation of around 1 nanosecond to a peak-to-peak variation that's maybe half of that in the 600 to 700 picosecond area. So a definite improvement just by leveling the 2 tones. Okay, that's all that's been done here. And we'll just take a quick look at the script file so you can see what I did in that file to accomplish this. So let's go to the Windows desktop, show the desktop, and open up this window for this optimizing power, and open the script file in Notepad and make it full screen. So I highlighted here with these little stars or asterisks what I changed. So all I did is I created a second channel to measure group delay, and in the second channel I offset the power of source 3. So the power, this is channel 2. It says source 2, but this 2 is the channel 2. This power is the power of source 3 or port 3. Okay, and I offset that power by 10 dB. That's the only change I made between the 2 channels. Otherwise I calibrate both channels and I measure the same thing. So that's what's happening in this file, and it shows that by bringing the power level equal, I can improve my measurement. So that's one thing one technique we want to take advantage of. And in particular, this equalizes what I saw in video 2 with respect to how I choose the optimal combining network. As long as I can use this coupler, and this coupler works great as a combiner, as long as I equalize these two tones. Now, this is for the source side where I'm driving the device under test, but as I mentioned, it's also important to optimize the receiver side. So I have another example where we can look at two different channels and see two different effects from changing another parameter. So let's pull that up with the GPIB Explorer script. So here I'm going to run a second script, which is called Optimize the Receiver Power Levels. And this is going to set up, again, two channels, ask me to calibrate the two channels. So I have the calibration mixer connected, so no problem. And then say, is it complete? Yes. All right. So now I have two channels again. This one where I'm setting the receiver gain setting of the receiver path to 0 dB. This is the default setting for the receiver. And in the second channel, I'm saying turn the gain of the receiver up by 10 dB. Make the receiver a little more sensitive on port 2. The reason I'm doing this is because my calibration mixer has a lot of insertion loss. So my port 2 receiver is operating at a lower power level than my port 1 source. So this is one way that I can take and equalize that effect, give us a little more gain in the port 2 receiver, which will help the signal to noise ratio. So just to confirm that this is doing what I think it's doing, let's first make sure the two tones are equal in both of these channels. So let's go to local, select the first channel, so it's highlighted, go to measure, two-tone group delay. Let's drag out the main tones to see if they're the same. Okay, so I have a lower tone and an upper tone. They're the same in this channel. Now let's highlight channel 2. And again, drag out the two tones, lower tone, upper tone, and they're also the same. So both channels have the same tone power. So that's not the difference between these two channels. Okay, what is different, let's get rid of these because we don't need them. What is different is this receive level setting. So this gain setting for the receiver. Now I can get at that setting by going to the mode key, and here there's an IF gain for the channel. So this channel 1 has an IF gain setting of 0 dB, and channel 2 has an IF gain setting of 10 dB. So all I'm doing is increasing the gain of the receiver in the second channel because the signal I'm receiving is much lower than in the second port than it is on the first port where it's going out. So by making that change, you can see I take my peak-to-peak level from somewhere in the 700 picosecond area, and I bring it down to about 200 picoseconds. So a further improvement in my measurement consistency or my measurement repeatability just by optimizing my power levels, equalizing the two tones, and optimizing the receiver level that port 2 sees. Now keep in mind, if my device under test has a lot of gain, then I don't want to turn up the gain on my port 2 receiver. Then I might, in fact, want to add attenuation to the port 2 receiver. So that can also be done by going to the power key. We have attenuators available on the B receivers. Now, if I activate this, it's going to start clicking. It'll sound like a machine gun. So I'll do it, and then I'm going to turn it off real quickly. But if my device has a lot of gain, then I might want to turn on the attenuator in port 2. I might want to set it to 20 dB, for example. And then that channel would have more attenuation on port 2 than what's on port 1. So depending on the conditions of my device under test, let's go back to 10 dB. If I have a lot of gain or a lot of loss, I need to optimize what's happening on port 1 and port 2 so that I have the best possible signal to noise ratio and so that I avoid compression on either port 1 or port 2 of VNA as well as in the device under test. So that is idea number 3, technique number 3 on my list of 10 ways to improve your frequency converting group delay measurements. It is to optimize your power levels.